Well, in this lecture, we're going to look at two examples of using the DFT to compute spectra or understand the periodicities or the frequency content of data. The first example that I want to look at is the sunspot activity measured over a number of years. So I've shown a plot here of sunspot activity, and you can see that starting in 1700 and all the way through the 1980s or so, we have these graphs that show how the sunspot activity changes with time. And you see that it appears to have some periodic aspect to it, and there is a period that coincides with most of the peaks, and then there also appears to be some slower periods in the data as well. So we're going to use the DFT to analyze this. And the first thing I'm going to do is just take the DFT of the data itself using MATLAB's FFT command, and we'll display that. So in this case, I chose 1,024 samples, and this corresponds to sampling the DTFT at 1,024 points. And what we have here is symmetry about the point 511, which corresponds to the fact that MATLAB samples the DTFT on a range of 0 to 2 pi. So these upper indices represent actually the negative frequencies. It's the range from pi to 2 pi, which of course is the same as the range from minus pi to 0. We see a very large term in the vicinity of 0, and this corresponds to the average value of the time series, because when you're counting something, it's always going to be positive. Okay, so we have a fairly large average value. We can ignore that. And then we see that there's this cluster here at DFT index around 100, and we can replot this using frequency as the axis, which I've done here, and our units now are in cycles per year. You see that there's a peak at around 0.09 cycles per year. And then there are some, various other peaks in here, but this is the dominant region, is in this vicinity of 0.1 cycles per year. Well, we can translate that to period, because period is 1 over the frequency, and here I've replotted it using an axis of period in years. And so that dominant peak, which is that 0.09 cycles per year, translates to a dominant period of about 11 years. There's some other periods in that same vicinity around 10. And then we also notice that there appears to be some secondary or weaker components that show up at 22 years, and then as well in maybe 27 or 28 years. Okay, so we can analyze the frequency of the sunspot activity using the DFT. Now the next example is a call of a loon that was recorded, and you can see the time series here. Now there's a lot of samples. I'm showing you 6 seconds, and this was sampled at 11 kilohertz, so the details are a bit obscured in here, but you can see the overall envelope of the call, and it looks like it's going to rise in volume and then decay and then rise and then decay and so on. And we'll listen to that now. So you could hear the rise and fall of the volume. Now we've computed the spectrogram, which is obtained by taking the DFT of individual sections of the data. And what you see here is time on this axis and frequency in hertz on the vertical axis. Initially, there were a few wing beats that you could hear if you listen closely that show up initially. And then here we have the initial rise of the call, and you can see the harmonics. Here's the fundamental, and here's the second harmonic, and there's a bit of a third harmonic. And then as the pitch rises, again we have a first harmonic at around 1,000 hertz, and then a second harmonic and a third harmonic. Eventually we have this sort of on and off pattern that we could hear in the sound, and you can see how the frequency is shifting over time. So those are a couple examples of using the DFT to analyze the frequency content of data. I've made the MATLAB code that I use to run these examples and the data available so you can try them yourself and explore perhaps changing some parameters and so on.